Hi everybody, welcome back. In this notebook, we're going to take a look at another architecture called UNet, which was developed at about the same time as the FCN architectures. We still have the concept of fully convolutional layers that encode feature maps and then decode them to produce the final segmentation map, but unlike the FCN architectures that used a specific backbone to perform the feature extraction, the UNet architecture implements its own feature extraction with additional lateral connections between the encoder and decoder portions of the network. This particular network was first used to perform segmentation of biomedical images, but of course it could be used for many other types of images. And in this notebook, we're going to implement the UNet model from scratch and see how it performs on the KITTI road dataset. In this section here, we're setting up several training and dataset configuration parameters, and notice that there's just two classes and that the image size is 224 by 224. We've already covered the detailed modeling of the UNet architecture in a previous video, but let's just take a quick look at the actual implementation in the function below. First, notice that the function has two required arguments, which are the number of classes and the shape of the input. And then we have several convolutional blocks which make up the encoder portion of the network, which are then followed by several decoder blocks. And notice that in each decoder block, we're concatenating feature maps from the decoder portion of the network with feature maps from the decoder blocks. And this is what we refer to as lateral connections because we're combining previous feature maps with downstream feature maps. And then in the final layer of the architecture, we're using a one-by-one convolution to limit the depth of the output to the number of classes, and we're passing the output of that through a softmax activation function. Since this particular data set only has two classes, we could have formulated the model to use a sigmoid activation function, but using a softmax activation function with two classes works just as well and allows us to use the same code with other data sets that contain more than two classes. One other thing we wanted to mention here is that the original description of this architecture didn't contain any dropout layers, but we've added dropout layers at each convolutional block for this particular problem to mitigate the effects of overfitting since we have a fairly small data set. So now in this next code block, we're going to generate the model by passing in the number of classes and also the shape of the input image. And here you can see that we're printing out the model summary, which contains over 31 million trainable parameters. And then further below, we have several sections of code that we've previously reviewed, starting with downloading the dataset, along with a description of the preprocessing required, a custom data loader class, and several helper functions and utilities. And then here we're using the custom data loader class to create training and validation dataset objects and displaying a few of the images from the training set. Here we're defining the IOU metric that we're going to use to assess the model, and then further below we're compiling and training the model using sparse categorical cross-entropy loss. And again, all of this is the same code as in the previous notebooks, so let's go ahead and scroll down and take a look at the training plots. If you recall from the previous FCN results from the last two notebooks, the accuracy that we get with the UNet model is about the same, although it takes a little bit longer for it to ramp up initially. But after about 50 epochs, the accuracy between the two models is nearly identical at just over 97% mean pixel accuracy. Notice that we're now also plotting the mean IOU accuracy metric, which in this case is also very high, but as we'll see with more complex data sets, there's going to start to be some disparity between the pixel accuracy and the mean IOU. And we'll be paying more attention to the IOU metric since it has a normalizing effect and is not biased by the percentage of pixels in any particular class. So generally, the IOU metric is a better way to assess the performance of segmentation models because of this. And then it's also a good idea to take a look at the loss curves just to make sure that they're tracking well together as shown here. And then finally, we have the same bit of inference code that we've used in previous notebooks. So let's just take a minute to scroll through the results and take a look at several different images. Notice that in some cases, the model actually performs quite well, but in other cases, it does have some difficulty in identifying the edges of the roadway. But again, very similar accuracy to the FCN model, although the failure cases between the two will be a little bit different. Later on in this module, we'll revisit this data set with a third model called DeepLab v3+, But before we do that, we're going to take a look at how the UNet model performs on a more difficult segmentation problem using the CAMVID dataset, which contains 32 different classes. And for that purpose, we'll also be using the dice loss function that we developed in the previous notebook.